distribution and application and service support for the high-end technologies in the field of the life science. Me personally, I am a specialist for the flow cytometry systems. For this technology, we cooperate with two companies at the moment. One of them is the company Amnis, working with the imaging flow cytometry, very high-end analyzers of the cells. This is my first presentation I would like to speak about today. Well, my second presentation will be about cell sorters. Please feel free to ask me anytime in case you would be interested for any particular part of my presentation. And also, in case I would speak too fast, please feel free to slow me down and our company cooperates with the company Amnis since 2009, but company Amnis works from 2004. They are based in Seattle, United States. From the time they installed and successfully worked several hundreds of instruments all over the world. Their main idea was to integrate the flow cytometry together with the microscope. Build a system based on the fluidics and mechanism of the flow cytometry with the camera detection, so detection similar to the fluorescent microscope. At the moment they have two units, smaller units called flow cyte, equivalent to the standard flow cytometry, and the in-stream system with the high resolution imagery for image-based analysis and application. So the main idea behind developing those systems was to find the value that imagery could bring to the standard flow cytometry, and on the other side bring the value of population statistics to the applications of the fluorescent microscope. In general, these systems are very powerful protocol development tools, but more about them a little bit later. These systems would not only objectively and statistically analyze the cells based on their intensity, but also based on their appearance. Over the years, this technology proved to be very successful as for publications. The number of publications steadily grows. Now we are somewhere between 500 and 700 publications. Some of them are also in a very high-ranking journals, as Journal of Virology, Journal of Immunology, or the Nature. So as I already mentioned, the main idea was to create a system which would combine the advantages of both standard flow cytometry method and the fluorescent microscope. Standard flow cytometry is a very well established and by years proved technology which provides a quantitative data for multiple probes working on per cell basis. However, it lacks morphology. We have no idea where the signal comes from. Does it colocalize with another signal? Or how the signal gets organized inside the cell? Morphological changes. On the other hand, the standard fluorescent microscopy, very well established technology, very powerful. Again, the Amnis is not trying to replace standard microscopy. It has an extremely high resolution of the images. It can work on per cell basis for multiple fluorescent probes, again for multiple signals. However, it is very difficult to get statistically large sample for some analysis. In case that you have a uniform cell line and all the cells there are the cells of your interest, then probably to get between 200 to 500 cells will not be such a problem. You will just stay a long time next to the microscope. However, if you get a heterogeneous sample where not all the cells there are the cells of your interest, or if you would like to observe some biology in a very, very rare cell subpopulation, then it might be a problem. And the second big issue is the difficulty to objectively quantify the visual changes in your images. So this is what the imaging fluocytometers, this is what the company AMIS wanted to do to prepare a system which would objectively and statistically be able to analyze and discriminate to cells based on the appearance and based on the intensity to achieve a high information content and high statistical power and of course also a high speed of imagery. So I would like to show you a little bit how the system works. First a little bit from the technical side, so that you have an idea how the system was built. And then my second part will speak a little bit about the about the applications. So what all you can do with such a system, and what would be the advantage using such a system in the long run. So this is pretty much how the system in very easy-fied blueprint works. As I already mentioned, the fluidic part is very similar with the standard flow cytometry. So the sample is being taken by the sampling port and driven by pressure through the tubing into the flow cell, where it's hydrodynamically focused in the core, where the cells are being illuminated by the series of excitation lasers, again equivalent to the standard flow cytometry. The cells are also being illuminated by a white light for the white light microscopy image. The whole images are being magnified by an objective lens and decomposed in the series of semi-permeable mirrors, which would decompose the signal based on the different spectral bands, different wavelength ranges, into the 6 different detector channels of the camera, detector camera. So as a result of such an analysis, you would get a series of images, either 6 or 12, where one of the images would be the bright field image, which is equivalent to the standard white light microscopy. And from that image is calculated the overall size of the cell, shape, and a couple of morphological features. Then you would get something called a bright field image, a dark field image, or a side scatter, which is being involved by a special laser, 785 nanometers. And this is equivalent to the granularity measure of the flow cytometer, side scatter. And then you will get the series of images based on your fluorophores you used for labeling your cells. So in this case, there is the fluorescein labeled nuclear factor kappa B, Psi3 labeled CD 14. CD400 couldn't be CD14. Very well. CD45 and the DREC5 as a nuclear marker. But this is not the only outcome you get from such an analysis. The images are just one part. The second part, of course, is also the standard flow cytometry data. So you get the overall values of all the intensities, and on top of that, a couple of morphological features for each fluorophore, and also population statistics. So this is how the system would look like all over. You have a wide choice of the fluorescent excitation lasers, multiple magnification, and either one or two camera system. A little bit about parameters. The system can analyze up to 5,000 cells per second. And this is a little slower than the standard flow cytometer. However, if we keep in mind that the system does about 12 images per each cell, then we actually acquire about 60,000 high-resolution images per second, which is quite good. Up to 5 excitation lasers, the emission spectra covers all the fluorophores today available at the market, and it's possible to equip the system with the auto sample. From the previous version, the older image stream X, the fluidics got improved, and now more than 95% of the sample is being utilized, which unlocks new applications like, for example, circulating tumor cells and the very rare cell subtypes. What I've prepared here for you is a comparison of the sensitivity based on the Spherotech ATP calibration reagent for the sensitivity between a high-end flow cytometer nowadays, VD4 and the flow cyte as the small system with low resolution. So as you can see, for flow cytometry data, VD4 has a great resolution of all 8 peaks, as well as flow cyte does, in a green and yellow spectra, so no problem here. However, as you can see in the orange, but especially red spectra, you can see that the flow cyte still keeps a great resolution even in the last couple of weeks. So the sensitivity here is really great and surpassing the top of the recent flow cytometry devices on the market. So that would be a little bit about the technical part. And now a little bit about the applications. Very basic advantage of having images is the visual confirmation. So you are able to display any single cell you would get, or any single groups of cells into the images, so you can visually verify that the images you are looking at are the cells you really want to work with. Flow cytometers really don't need that for some standard applications, like this is the 5-part white blood cell differentiation based on CD45 and site scatter from the blood sample, so it would very nicely distribute to the lymphocytes, neutrophils, eosinophils, monocytes, and basophils. And you are able also to optically visualize, based on the imagery, that the groups which were differentiated for you are really the cells of your interest. So based on the nuclear morphology of neutrophils, you can see this very typical shape of the nuclei, this kind of polylobe structure, very typical for neutrophils, or this very typical kidney shape nuclei for monocytes. And that's, by the way, how those white blood cell types were identified in the first place, by the morphology of the neutrophils. But this is something very basic. The second step is that you can, based on the nuclear morphology, statistically sort and statistically express and describe these different groups. The second, okay. So this is with my laptop, so I don't. Yeah. Okay, usually closing the thing solves the problem. This would be, let's say, the main advantage of having being able to see what you are getting from your scatter plots. So again, standard blood sample, peripheral blood, where as in flow cytometry, we would differentiate the forward scatter, side scatter required leukocytes, and from the leukocytes based on the CD14 marker, CD16 marker differentiate the monocytes and the neutrophils. So this is something a standard flow cytometry does on a daily basis very easily. So ImageStream gives you the same kind of data, but the interesting part starts when you get the populations you are not supposed to see. So for example, something like here, it's not really usual that the cells would be even CD14 and also CD16 positive, double positive. So we are not really expecting this kind of population. Or something like this. So there is actually nothing more easy than just to does it work? Maybe I need to click on it. Yes. Okay. So monocytes, neutrophils, and those are the populations I spoke about. So you can actually see that our double positives are actually the doublets we weren't able to get out during our basic gating. So you can actually see that the monocyte is stuck to the neutrophil. So this is something we are not that interested in. Or maybe we are. Actually with the ImageStream it's possible to do the doublet analysis. There are the immunologic sites where they are looking, for example, on the immune interactions between the T cells and the B cells. And here you can actually gate specifically on the doublets and observe the changes, the biological changes, for example, in the T cell. One of the applications would be the migration of the adhesion compound of the T cell from the cytoplasm to the place of the immune synapse. Right. So what I wanted to show you here is that you can be very confident in what is your sample, what are the cells of your interest, and what are just artifacts which need to be eliminated from your analysis. This can be very useful, especially if you are starting a new experiment. If you are not following just a protocol which has been established 10 years ago, but you are trying a new cell line, you are trying a new staining, you are trying a new permeabilization method, then you really cannot say if it works and if the staining is nicely specific on the surface or if it unspecifically stains your cell. Here you just display the cell, have a fast view, you can tell from the beginning, yes, those are the cells I want to use, or no, my new antibody doesn't work, I need to return it and buy it from somebody else. So this is what is meant by an excellent protocol development tool, especially if you are looking for something new, it can be a great helper. My second part of the application would be something which a flow cytometry does on the daily basis. I'll show you how the ImageStream can do not only the similar or the same data, equal data, but we can get on top of that a couple of more information. So cell cycle in the PHP1 cell line, and as a standard flow cytometry, even a UNMIS gives you the very typical histogram based on the intensity of DAPI. DAPI nuclear staining, the overall intensity is translated to the overall DNA content. So our cell line would have the G1 phase, cells in G1 phase, cells in the S phase, and cells in the G2 and N phase. This analysis was done using the FlowJo on top of the data acquired here, but with the percentage. So this is something the standard cytometry would give you as well. However, we can look a little bit deeper into our cell line, look at the texture of the DNA staining, and based on the high texture differences, differentiate the G2 phase and M phase, the mitosis phase, and identify and statistically express at different stages of mitosis, like prophase, metaphase, anaphase, and telophase. Here, always in comparison with the white light microscopy image, you can see that the cell is already divided. So this is something you can't get from standard flow cytometer. But the reason why people usually buy and use image stream in the first place is to combine a standard flow cytometry experiment with something more, with looking into the actual biology of the cells. So applications like cell signaling, internalization and phagocytosis, surface intracellular colocalization, immunologies, especially cell-to-cell interaction. Okay, so cycle and mitosis, we have just seen that. There is a couple of genetical applications like fluorescence in situ hybridization. It's possible to look on the thread applications, or some people use it for oceanography. They look at the morphological differences between the microflora in the coastal waters. Based on this, they do the identification of the specific subtypes of the microflora, and based on that, they assess the quality of the coastal water. So there is really many applications. Let me show you one based on which I will try to show you how the instrument works and how it nicely combines the standard flow cytometry application with something a little more. We will look at the cell signaling. Okay. But before I will go there from the point of view of the flow cytometer, let me look at the same issue. Something wrong. Okay. In this experiment, we do have the monocytes, isolated monocytes, and they are incomplete stimulated by lipopolysaccharide. Particle from the bacteria cell wall, which is inducing immune response in the monocytes. This bacteria cell wall particle, this lipopolysaccharide, would induce immune response, which would be shown as a translocation of nuclear factor kappa B, from the area of the cytoplasm into the nucleus to start the producing some immune particles and so on. So this is a sample of the incomplete nuclear factor kappa B translocation, and this is basically what you would get under the fluorescent microscope. And now, could you tell if this sample is more translocated or more untranslocated? How would you even objectively assess such an issue? You would say, okay, this sample is, these cells are untranslocated, so it's untranslocated. Or somebody else can come and say, this and this is translocated, the nuclear factor kappa B is in the nucleus, so who is right? So that's what the image-based features of this system do, is that they, I'm sorry, they compare the intensities in each pixel of the cell, and they are looking at the nucleus, and they are asking, is in the nucleus the high intensity of the nuclear staining? Well, usually it is. But is there at the same time in the same pixel, over about 500 pixels per cell, so it's in the same pixel also the high intensity of the nuclear factor kappa B state? If yes, it results in a high similarity score. If no, it results in the negative similarity score. And you get such a profile, such a, let's say, histogram, but not based on just intensity, but on the comparison of intensities, in this case called similarity, an image-based feature. In this kind of experiment, it's very, very important to have a negative biological control to observe how this profile shifts from completely untranslocated to translocated images. Let me show you how this thing was measured based on the image stream X. But this time, to be a little bit more difficult, this was not an isolated monocyte. This was the whole blood, which was incubated in liquid polysaccharide. First step to identify a different white blood cell types was the immunophenotypization. So each one white blood cell type of the interest, in this case it was neutrophils, monocytes, and the T cells from the lymphocytes. So they were immunophenotypically stained. So we have that four-color immunophenotypization, and the staining was also done for the nuclear factor kappa B and for all the nuclei. It was collected 20,000 cells at the 60x magnification on image stream. And they were trying to quantify the nuclear localization in the whole blood substance, in those different types. So this immunophenotypization was done on CD14, CD45, CD16, and CD3. So monocytes, CD45 are lymphocytes T cells, and CD16 neutrophils. So, based on this, different white blood cell types were identified. So neutrophils, first you can see a very nice typical nuclei shapes, but of course they were gated based on the CD16 expression. The eosinophils have the furthest, highest site scatter granularity. Monocytes are CD14 positive and a little bit CD45. However, the T cells would be very high on CD45 and also positive for CD3 marker. So the different cell types were gated. And based on those gates, based on those populations, they were looking into the cell signaling in each of them. They were looking in each of those types whether the nuclear factor kappa B will translocate from the cytoplasm into the nucleus after stimulation with lipid polysaccharide. So they have the negative control with the untreated cells, where you can see that the similarity scores are mainly around 0 or negative, so not really a big translocation happening, neither in monocytes, neutrophils, nor T cells. However, after stimulation with lipopolysaccharide, you can see that the monocytes in yellow specifically responded in comparison with the neutrophils and T cells who didn't react on such a stimulus. So the question is, could you do such an experiment with the standard flow cytometer? Not really, because you would get up to the point that you would identify a different cell populations, but the overall DNA content is the same. The overall content of nuclear factor kappa B also doesn't change, just the localization. Doesn't work. Okay. So this was one of their pilot applications they started in stream with, but by far this is not the only one. There has been done a whole bunch of experiments. I have here another. For the time reasons, I will go just very, very quickly through it. This is the experiment with the plasmacytoid dendritic cells, very rare cell subtype. Now they linked with the production of the antiviral interferon alpha, and so on. But in this case, they would look on the ability of those plasmacytoid dendritic cells to incorporate a viral DNA particle and to digest it. So how the experiment went, they would incubate again the whole peripheral blood, where those plasmacytoid dendritic cells are only about 1/10 of the percent among all the white blood cells, and incubated with the viral-like particle. CpGB is an artificial construct of the DNA which is similar to the viral DNA. The cells, of course, were first immunophenotypically stained on the surface protein BDCA, specific for plasmacytoid dendritic cells, and of course, the viral-like particle is CpGB was stained, and then they stained also the endosomes and lysosomes, and they were looking in the time manner how the viral-like particle moves. So they were looking on the internalization into the cell, and they were looking at co-localization of the signal from the viral particle to the endosomes and to the lysosomes. So they collected about 20,000 cells, and this is what they have got. This is a chart with incubation of 30 minutes. Where? Sorry. Jumping. No. Too fast. Yeah. Where at the x-axis there is again the similarity, looking at the co-localization of the signals. In this case, CD107A is a lysosomal marker. And on the y-axis is the internalization. It's looking, is the red signal within the area of the cell or outside? So the low internalization scores, of course, cells are, single cells are triple positive, but the red dots are outside of the cell. So this viral-like particle is just a touching on the cell. In this quadrant, the viral-like particle is inside the cell already. Internalization score is high. However, it is not co-localized to the lysosomes. While in this part, you can see that the viral particle is inside and also co-localized to the endosomes. Sorry, lysosomes. If you look at the experiment as it went the whole time, you can see the negative control to prevent internalization. Then you can it's jumping too fast. And then you can see up the endosomes and at the bottom the lysosomes and the percentage of their co-localization. So from such a data, the people who performed this experiment actually concluded that originally this viral-like particle is being internalized into the endosomes, and after the course of time traffics from the endosomes into the lysosomes. So this data highlights several strengths of the image stream. That's the combination of the standard flow cytometry methods like immunophenotyping with the correlation of two different fluorescent images, which allows us to measure colocalization and internalization of molecules, proteins within specific subsets. Something a little bit about the equipment of the system. I'll go very, very fast through that. The selection of the lasers is very similar to what the standard flow cytometry has to offer, from the UV spectra up to the red spectra. As for the staining can be is again not difficult, not different from the standard flow cytometry. Even the sample preparation, the samples are just being prepared in the same way, and each detector channel of the camera has its specific range of the fluorescence wavelengths in which it collects the signal. So all the possible available staining is to be used on image stain. There is a possibility to, beside the standard 40x objective, to have an interchangeable objective stack with 20x for fast screening or for analysis of the large objects, or the 60x objective for a very, very detailed analysis of cellular substructures with the resolution of the pixel of a 0.33 micrometers per pixel size, which makes 0.115 micrometers squared per pixel area, which gives us for the standard cell something between 200 and 500 pixels. Right. My last remark would go according to the couple of novel genetic applications like fluorescent in situ hybridization, which is possible to be done on image stream with a special optical upgrade for being capable of increasing the depth of field of the objective from about 4 micrometers square up to about 4 microns to up to 16 microns in diameter, which would change the imagery from a standard one up to the very nice crisp imagery for spot counting, allowing us to count the fish spots in our experiment, or for example nuclear foci. In this case they were measuring the irradiation of the lung carcinoma. So, a couple of words for the conclusion. The systems nowadays are very well used in the fields of immunology, oncology, cell biology, genetics, oceanography, hematology, pretty much everywhere where the standard flow cytometry or fluorescent microscope takes place. In the end, I'd like to show you, this is the map of the Europe, and the blue parts are the area where we cooperate with the company Amnis, or now they are actually part of the EMD Millipore from 2012. So in this territory for our 3 years of cooperation, we have installed about 13 units, both image streams and flow sites, where people are working on a daily basis. A couple of those installations are quite successful with the publications in regional and also international journals. So I thank you for your attention. I'll be happy if you would have any questions regarding this technology. Yes?
Can this device separate cells like cell sorter?
It is not a sorting device, it is just analyzing.
Can this device measure the electronic volume of cell, you know, like in Beckman-Coulter
yes, it does have the volume measurement, so you know how many cells or in what volume the cells were measured.
The Beckman-Coulter devices can measure the electronic volume, which is something like a size of cell.
For the size measurement you can get from the image stream, it would be the overall area of the cell in the micrometer square, and you would get its total length, total width, and also several shape features like the width divided by the length, which would give you some idea about elongatedness, as much as for the shape of the cell. Then of course you have much more possibilities to work with the fluorescence.
Okay.
So it is actually possible to do such a estimation like the Beckman Coulter does based on the area of the cell. Mm-hmm.
Did I get you right that you mentioned the amount of photographs, something like 60,000 per second. This device does store this giant amount of data all the time you measure it, and the images of the cells which are on most of your slides, do they get automatically visualized so you can tell it's a monocyte, not turning all the 60,000 photos?
Yes. How the acquisition process works is that you are getting. Let me go there very fast. I have really many slides. Okay. I think that this will be sufficient.
Yes.
So when you are acquiring, in the process of acquiring, you are getting randomly sampled about 20 or 30 cells per second, and you get their images. And you can gauge based on several features like intensity, for example, or several shape features. So you can, for example, create such a histogram like for a scatter plot, like a CD45 against side scatter. Find your monocytes. You will just gauge on them, and you should see all those cells which are being acquired as a monocyte, so you can actually see them if they are really monocytes. Or you can just gauge on any population and visualize it before you actually acquire it. And that's usually where people find the cells of their interest and decide to acquire just a certain gate, not maybe everything. But even it is possible to acquire everything and then to get rid of the rest of the data in the analytical software. This acquisition part, this allows you to work only with a couple of parameters like intensity, like some basic shape, and all the image-based analysis is taking place after acquisition on a powerful workstation, computer workstation, which comes with the system for the analysis.
Another question, please. The part where you mentioned the intrusion, I didn't quite get for example, on the artificial virus part, when you, how do you tell that viral part or something else gets inside the cell in the nucleus and not at top of it, aside of it?
This is a good and very correct question. Let me address that. In case that you have such an image here, and you see the red dot kind of inside, you can't really say with 1000% that it's inside and it's not on top of that.
Yes.
That's true. The way the standard microscopy approaches this is that it would do a couple of Z stacks by a confocal and look in each level if it's really inside. Well, here we approach this issue from a little bit different angle, from the statistical point of view. You cannot say that this particle here, in particular, is really inside. However, what you can say is to look at your negative control, which is here. And you can look at your incubation processes, and you will see the drift in the internalization. So you can say that, for example, in comparison of this and this, you have about 80% drift based on some biologic stimuli. You cannot say exactly that one signal in that one cell we saw is exactly there or not, because for that reason you would really have to take the confocal. But you can say, in comparison with your negative biological control, that the whole population reacted on your stimulus. Because we can say, okay, 1% can be artifact, 5% can be also artifact. But we are not speaking here about 5%, we are speaking here about 80%.